Hey Geometry, today we're going to get into section 7.2, which is for similar polygons. We're going to start with some example of some similar polygons we've seen. A typical movie screen is 45 feet wide by 25 feet high. If you compare the movie theater screen to two different home televisions, which TV screen format shows the most proportion of the movie similar to the theater experience? So the theater experience is 45 feet wide by 25 feet high. And so that's our movie screen. And so what we're talking about here is actually aspect ratio. So you may have seen this before. So we could do it this way. We could do 45 feet per 45 feet of width per 25 feet of height. If we reduce that fraction, we can divide both of those up. And so we can divide that by 5 and we get 9/5. And so that's we might call that a 9:5 aspect ratio. We can also do this. Notice that I'm doing this one in feet and these ones are measured in inches. So let's see how this works out differently. What if I converted these to inches? So 45, if I multiply that by 12, we get 540 inches. And the same thing here, if we do 25 by 12, multiply that by 12, we get 300 inches. Well, we can do the same thing. We can do 540 per 300. And what do you know? If you reduce that fraction, 540 divided by 300, all right, you get a decimal, but math frac will save us from having to reduce ourselves. 9/5. Of course, we could look for things we could divide the numerator and denominator by. Get that exact same ratio, whether we're in feet or inches, or whatever unit you want to use to measure, that ratio is going to be the same. So we've got a 9/5 ratio here in our theater. Let's see how that compares to these. We can do 36 to 27. And notice that I'm doing width to height. So I'm doing, that width to height ratio. You could reverse that. You could do height to width. It would just be then 5 to 9 ratio. And so it doesn't matter, but yeah, we'll go width to height. And so if we reduce this one, 36 over 27, that one reduces to 4:3. That's a 4:3 aspect ratio. Notice that fraction doesn't quite match that, and we could see what the ratio is off of those, but 9/5 does not match 4/3. Over here, though, if I have a 36 by 20 inch, notice this screen's a little smaller, so it's the same width, but it's the 36 to 20, so that will be 36 per 20. If we reduce that fraction, that one actually goes, if we divide both by 4, we get 9/5. So this screen exactly matches this one. So this is the one that matches it better. Now that said, it's kind of interesting. This one will show that movie. That what they'll just do is have those black bars at the top and bottom. But ultimately, so like this one perfectly matches. That's what they're going for. But this one will actually end up showing the exact same size screen as this. It'll just have blacked out at the top and bottom of that screen, which may not be ideal. All right, so you can use corresponding angles and corresponding side lengths to decide whether two polygons are what we call similar. And find unknown side lengths of similar figures. So this is kind of similar to, we talked about congruence a lot. Congruent means like exact same, right? Same. I mean, maybe different orientation and things like that, but it's all the angle measures are the same. All the side lengths, the corresponding side lengths are the same. So we can do something similar here, but we're talking about similar shapes. They're not the exact same. So we call them, two polygons are similar if and only if their corresponding angles are congruent. So they have the exact same angles, but the corresponding side lengths are proportional. So the side lengths don't have to be the same, but they're proportional to each other. And so here's a picture of what this could look like. Notice that my side lengths are different, that this figure here is bigger than that figure. So they're different sizes, but the angle measures are the exact same, and so they are similar shape. And really, you can think about this as a dilation from when we did transformations. So those figures we call similar. The angle measures are identical. Notice we marked those as congruent, but the side lengths are proportional. So here we use this symbol. This is the symbol we use for similarity. Remember, congruence has got the squiggle with the equals. This is just, and so we've got that there, but this is just two similar figures. ABCD is similar to WXYZ. The corresponding angles, A is congruent to angle W. A is going to be congruent to angle W. B is congruent to X. B is congruent to X, and so on. The angles are congruent. The corresponding sides are proportional. So if we take like side AB, the first pair of letters there, that should be proportional to WX. So AB over WX, that ratio, AB, whatever AB is, 15 over 5. That ratio should exist throughout. And 15 over 5, notice that reduces. If we divide, we get 3 over 1, so 3 to 1 ratio. But that should exist in all pairs of sides, so 15 over 5. And then we can have BC XY, which would be 12 to 4. 12 to 4 also reduces to 3 over 1. 21 over 7, 18 over 6. All four of those fractions have to have that same ratio, and that's how we would call those figures similar. So in this one, we want to make sure we understand it. Remember, we write these similarity statements similar to congruent statements where the corresponding letters are written in the same position. So the first letter is congruent to the first letter in terms of angle. So I know angle A is going to be congruent to angle W. We know that angle B, do a couple lines there, is congruent to angle X, and so on. All right, C, and 4 lines there. Getting a little excessive, but that's the idea there. Those are the corresponding parts. So I'm going to write that out as well because they did want us to write this out. List the pairs of congruent angles and extended proportion that relates to sides. So the angles, I know angle A is congruent to angle W. I know that angle B is congruent to angle X, C to Y, and D to Z. So those are the congruences. But these figures aren't the same size. They're different sizes. And so I should have AB be proportional with WX. So AB, the length AB over WX, should be equal to the length BC over XY. BC over XY. Those should be in the exact same proportions. I don't actually know what they are. I don't know, like over here I knew it was 3 to 1 in that example. I don't know what it is here. They didn't give us any numbers, but those fractions should be identical. And the same as CD to YZ, CD per YZ, and AD to WX. Notice that not WX, WZ. Put that wrong. Notice that I always went left triangle, or left quadrilateral, left to right. I'm just going to say I did that way. But you could have done this the other way. These fractions all should still match if you flip them all, if you go right to left. So WX to AB should match XY to BC, and should match YZ over CD if you flip all of those fractions. All right, similar one here, smaller with the triangles. We've got triangle MNO, RST. So M corresponds to R. So angle M is congruent to angle R. So I'm going to write that up here. Angle M is congruent to angle R. And then N goes with S. So N goes with S. Angle N is congruent to angle S. And finally, O to T. Angle O is congruent to angle T. 3 lines, 3 lines. All right, but then we want to write out this extended proportional fraction for the sides. So MN, those first two, MN over, and then that goes with RS. I could look at the triangle and see, it goes from that 1 congruence marking to 2, 1 to 2. That fraction, that ratio, should match NO. I'm just going to do the second letter, third letter, ST. You don't actually need the picture to help you with this. You can just do it all from the letters up here. NO is the second and third letter, ST. And then the last side is, you could either say MO or OM, whatever way you want to do that. OM, and that's the third to first, TR. You could look at it in the pictures as well. MN, again, I went left triangle to right triangle. MN over RS. NO over ST. OM over TR.